The Milky Way is the vast galaxy that contains our solar system, meaning every planet, moon, asteroid, and comet we have ever observed resides inside this immense cosmic structure. When you look up at the night sky far from city lights, the faint glowing band you see stretching overhead is actually the dense disk of our galaxy viewed from within. We are not observing it from the outside. We are embedded inside one of its spiral arms. The Milky Way is classified as a barred spiral galaxy. This means that instead of having a simple round core, it has an elongated central bar made up of stars. From the ends of this bar extend sweeping spiral arms that curve gracefully outward. These arms are not solid structures, but regions where stars, gas, and dust are more densely concentrated, giving the galaxy its beautiful pinwheel-like appearance. Our galaxy is enormous in scale, measuring roughly 100,000 light-years across. A light-year is the distance light travels in 1 year, about 5.88 trillion miles. That means if you could travel at the speed of light, which is about 186,000 miles per second, it would still take 100,000 years to cross the Milky Way from one side to the other. The Milky Way contains somewhere between 100 billion and 400 billion stars. Scientists give such a wide range because it is extremely difficult to count stars in a galaxy from the inside. Dust clouds obscure our view, and faint stars are hard to detect at great distances. Even so, the lowest estimates still place the Milky Way among the larger galaxies in the universe. Our Sun is located about 26,000 light-years from the galactic center. It sits in a minor spiral arm called the Orion Arm, sometimes referred to as the Orion Spur. This region is not as massive as the galaxy's main arms, but it still contains thousands of stars, nebulae, and stellar nurseries where new stars are actively forming. The Milky Way is not static. It is constantly rotating. However, it does not rotate like a solid disk. Stars closer to the center orbit faster than those farther out, yet not in the way classical physics alone would predict. This unusual rotation pattern is one of the key pieces of evidence for the existence of dark matter, an invisible substance that makes up most of the galaxy's mass. It takes our Sun approximately 225 to 250 million years to complete one full orbit around the galactic center. This journey is sometimes called a cosmic year or galactic year. The last time Earth was in this exact position in the galaxy, dinosaurs had not yet appeared. Humanity has existed for only a tiny fraction of a single galactic orbit. At the very center of the Milky Way lies a supermassive black hole known as Sagittarius A*. This object has a mass about 4 million times greater than that of our Sun. Although black holes are often portrayed as cosmic vacuum cleaners, Sagittarius A* is relatively quiet, and it does not pose any danger to Earth due to the vast distance separating us. The central region of the Milky Way, called the galactic bulge, is densely packed with older stars. This bulge is roughly 10,000 light-years thick and contains some of the galaxy's oldest stellar populations. The stars here tend to be redder and older than those in the spiral arms, suggesting that this region formed early in the galaxy's history. The Milky Way is surrounded by a vast halo of stars, globular clusters, and dark matter. This halo extends far beyond the visible disk of the galaxy. Globular clusters are tightly packed spherical collections of ancient stars, some of which are nearly as old as the universe itself, providing clues about the early stages of galactic formation. Interstellar dust plays a major role in shaping what we can see of the Milky Way. Thick clouds of dust obscure large portions of the galaxy in visible light. However, when astronomers observe in infrared or radio wavelengths, they can peer through the dust and reveal hidden star-forming regions and the dynamic activity near the galactic center. The Milky Way is estimated to be about 13.6 billion years old, forming not long after the Big Bang. Over billions of years, it grew by merging with smaller galaxies and accreting gas from its surroundings. These mergers helped shape its spiral structure and contributed stars that now orbit within its halo. Our galaxy is part of a small collection of galaxies known as the Local Group. The largest member of this group is the Andromeda Galaxy, which is on a slow collision course with the Milky Way. In about 4 to 5 billion years, the two galaxies are expected to merge, forming a new, larger elliptical galaxy. The Milky Way's spiral arms are regions of active star formation. Giant molecular clouds within these arms collapse under gravity to form new stars. These stellar nurseries can produce massive, bright blue stars that burn hot and fast, living only a few million years before exploding as supernova. Supernova explosions in the Milky Way play a crucial role in enriching the galaxy with heavy elements. Elements like iron, gold, and uranium are forged in the cores of massive stars and during their explosive deaths. These elements eventually become part of new stars, planets, and even living organisms. The Milky Way emits radiation across the entire electromagnetic spectrum, from radio waves to gamma rays. Different wavelengths reveal different aspects of the galaxy. Radio waves highlight cold hydrogen gas, infrared shows warm dust, visible light reveals stars, and X-rays expose high-energy phenomena like black holes and neutron stars. Dark matter makes up most of the Milky Way's total mass. Although it cannot be seen directly, its gravitational effects are measurable. Without dark matter, the galaxy would not have enough visible mass to hold itself together at its observed rotation speeds. This mysterious substance forms an enormous invisible halo surrounding the galaxy. The Milky Way is not perfectly symmetrical. Its disk is slightly warped, meaning the outer edges bend above and below the central plane. This warp may be caused by gravitational interactions with nearby galaxies or the uneven distribution of dark matter within its halo. There are likely tens of billions of planets within the Milky Way. Observations from missions like Kepler suggest that many stars host planetary systems. This means the galaxy could contain billions of Earth-like planets in habitable zones, raising profound questions about the possibility of life elsewhere. Cosmic rays constantly travel through the Milky Way. These high-energy particles are often accelerated by supernova remnants and other energetic events. As they move through the galaxy, they interact with magnetic fields and interstellar gas, contributing to the complex and dynamic environment between the stars. The Milky Way is moving through space as well. It is not stationary, but traveling toward the center of the Local Group due to gravitational interactions. At the same time, the entire Local Group is moving relative to the cosmic microwave background, showing that motion exists on every scale in the universe. The Milky Way is not isolated in space. It has a system of smaller satellite galaxies orbiting it. These dwarf galaxies are gravitationally bound companions, slowly interacting with, and sometimes being torn apart by the Milky Way's immense gravity. One of the most well-known is the Large Magellanic Cloud, which is visible from the southern hemisphere and actively interacting with our galaxy. Another close companion is the Small Magellanic Cloud. Together with the Large Magellanic Cloud, it forms a trio of interacting galaxies. These dwarf galaxies are slowly losing material to the Milky Way, contributing streams of gas and stars that stretch across space like cosmic rivers. One of the most dramatic features discovered in recent years is the presence of massive structures called the Fermi bubbles. These enormous lobes of high-energy radiation extend above and below the Milky Way's central plane. They likely formed from past energetic activity near the supermassive black hole at the center, showing that our galaxy has experienced powerful outbursts in its history. The Milky Way contains vast amounts of cold hydrogen gas. This gas serves as the raw material for future generations of stars. Over time, gravity pulls this gas together into denser clouds, which collapse and ignite nuclear fusion. In this way, the Milky Way is both ancient and continuously renewing itself through star formation. Not all regions of the Milky Way form stars at the same rate. The spiral arms are much more active than the quieter regions between them. These arms act like traffic jams in space, compressing gas as stars orbit the galaxy. This compression triggers waves of star formation, giving the arms their bright blue appearance. The galactic center is an extreme environment. Stars orbit Sagittarius A* at incredible speeds, some moving thousands of miles per second. Astronomers have tracked individual stars whipping around the black hole, providing some of the strongest evidence that a supermassive black hole truly resides at the galaxy's core. The Milky Way has likely merged with many smaller galaxies in the past. Evidence of these ancient collisions remains in the form of stellar streams long, thin trails of stars that move together through the halo. These streams are remnants of galaxies that were stretched and torn apart by tidal forces over billions of years. The thick disk of the Milky Way differs from its thin disk. The thin disk contains younger stars, gas, and dust, while the thick disk is made up of older stars that orbit at slightly different angles. Studying these two components helps astronomers understand how the galaxy evolved over time. Magnetic fields thread throughout the Milky Way. Although invisible, these magnetic fields influence the motion of charged particles and shape the behavior of interstellar gas. They also play a role in star formation, helping regulate how clouds collapse under gravity. The Milky Way is part of a much larger structure known as the Virgo supercluster. Within this enormous region of space, thousands of galaxies are bound together by gravity. On even larger scales, galaxies form vast cosmic filaments and voids, creating a web-like structure that spans the observable universe. Our galaxy likely began as a smaller protogalaxy composed mainly of hydrogen and helium. Over time, repeated mergers and steady gas inflow allowed it to grow into the massive spiral galaxy we see today. Each generation of stars enriched the interstellar medium with heavier elements, gradually increasing the chemical complexity of the galaxy. The stars in the Milky Way come in many varieties. Massive blue giants burn brightly and die young, while smaller red dwarfs can shine for trillions of years. Red dwarfs are thought to be the most common type of star in the galaxy, meaning most stars in the Milky Way are smaller and cooler than our Sun. Globular clusters orbit the Milky Way in its halo. These densely packed spherical clusters can contain hundreds of thousands of stars. Many globular clusters are more than 12 billion years old, making them some of the oldest surviving structures in the galaxy. The Milky Way's disk contains large, beautiful nebulae, vast clouds of gas and dust illuminated by nearby stars. Regions like the Orion Nebula, located in our own spiral arm, are active star-forming regions. These nebulae provide astronomers with natural laboratories for studying how stars and planetary systems are born. The galaxy contains countless stellar remnants, including white dwarfs, neutron stars, and black holes. When stars exhaust their nuclear fuel, they leave behind these exotic objects. Neutron stars can spin rapidly and emit beams of radiation as pulsars, while stellar mass black holes quietly roam the galaxy. The Milky Way's gravitational pull extends far beyond its visible disk. The dark matter halo may stretch several 100,000 light-years outward. This means the true size of the galaxy is much larger than what we can see with optical telescopes. Astronomers map the Milky Way using radio telescopes that detect the 21-centimeter emission line of hydrogen. This allows them to trace the structure of spiral arms and measure how gas moves within the galaxy, even when dust blocks visible light. The galaxy is constantly evolving. Stars are born, live their lives, and die. Gas clouds collide and collapse. Black holes merge. Over cosmic timescales, the Milky Way slowly changes shape and structure, even though to us it appears stable and unchanging. The Milky Way contains regions known as superbubble's vast cavities, carved out by multiple supernova explosions. These energetic events push gas outward, creating enormous shells that can span hundreds of light years. Our solar system moves up and down slightly as it orbits the galaxy. oscillating through the galactic plane. This vertical motion takes tens of millions of years and may influence the flux of cosmic rays reaching Earth. The Milky Way is tilted at about 60 degrees relative to Earth's equator. This tilt affects how and when different parts of the galaxy are visible from different locations on Earth throughout the year. The brightest region of the Milky Way in the night sky lies toward the constellation Sagittarius, which points toward the galactic center. When we look in that direction, we are peering into one of the densest concentrations of stars in the galaxy. The galaxy likely contains millions of rogue planets, not bound to any star. These objects may have been ejected from their original systems during gravitational interactions. They drift silently through interstellar space, illuminated only by faint starlight. High-energy gamma-ray bursts have likely occurred within the Milky Way in the distant past. These powerful explosions are among the most energetic events in the universe and may result from collapsing massive stars or merging neutron stars. In several billion years, when the Milky Way merges with the Andromeda Galaxy, the night sky from Earth, if Earth still exists, would be dramatically transformed. Stars would shift positions, and enormous tidal streams of gas and dust would stretch across the heavens. Despite its enormous size, the Milky Way is just one galaxy among an estimated 2 trillion galaxies in the observable universe. Yet for us, it is home. Every human who has ever lived was born inside this vast rotating disk of stars, orbiting a quiet star in a minor spiral arm, part of a galaxy still unfolding its story across cosmic time. The Milky Way's spiral arms are named structures, including the Perseus arm, the Scutum Centaurus arm, the Sagittarius arm, and the Orion arm where our Sun resides. These arms are not rigid structures, but density waves that move through the disk. As gas enters these regions, it slows and compresses, triggering bursts of star formation that light up the arms with brilliant young stars. The Sun is located in a relatively calm neighborhood compared to some parts of the galaxy. Regions closer to the galactic center experience far more radiation, supernova explosions, and gravitational disturbances. Our position about 26,000 light-years from the center may be one reason life had a stable environment in which to evolve on. Earth, the Milky Way's central bar, is thought to act like a funnel, channeling gas inward toward the galactic core. This inflow of gas may occasionally feed the supermassive black hole at the center, causing it to flare with activity. Although it is relatively quiet now, evidence suggests it was more active millions of years ago. Astronomers believe the Milky Way has been cannibalizing smaller galaxies for billions of years. One example is the Sagittarius dwarf spheroidal galaxy, which is currently being stretched and torn apart. Its stars are being absorbed into the Milky Way's halo, adding to the complex structure surrounding our galaxy. The halo of the Milky Way contains extremely metal-poor stars. In astronomy, metals refer to all elements heavier than hydrogen and helium. Stars with very low metal content likely formed early in cosmic history, before many supernovae enriched the galaxy with heavier elements. The Milky Way contains an enormous amount of molecular hydrogen, often concentrated in giant molecular clouds. These clouds can span hundreds of light years and contain enough mass to form thousands of stars. Within these cold, dense regions, gravity slowly pulls matter together until nuclear fusion ignites. Our galaxy's rotation curve was one of the strongest early indicators of dark matter. Observations showed that stars far from the center orbit at nearly the same speed as those closer in. Without additional unseen mass, these outer stars should be flung into intergalactic space. The Milky Way produces about 1 to 3 new stars per year. While that may sound like a lot, it is actually modest compared to some galaxies known as starburst galaxies, which can produce hundreds of stars annually. Our galaxy is considered relatively calm and mature. The disk of the Milky Way is embedded within a much larger, spherical dark matter halo. This halo may extend up to 300,000 light-years from the center. Though invisible, It dominates the galaxy's total mass and governs its gravitational behavior. The Milky Way is gradually consuming gas from its surroundings. Streams of gas, possibly originating from dwarf galaxies or intergalactic space, fall into the galaxy and replenish the material needed for star formation. Without this inflow, the galaxy would eventually run out of star-forming fuel. The supermassive black hole at the center, Sagittarius A*, was directly imaged in 2022 by the Event Horizon Telescope collaboration. The image revealed a glowing ring of hot gas surrounding a dark shadow, providing visual confirmation of the black hole's existence and properties. Stars near the galactic center form a dense nuclear star cluster. This region contains millions of stars packed into a relatively small volume. The gravitational forces there are intense, and stellar interactions occur far more frequently than in our local neighborhood. The Milky Way's disk is not perfectly flat. It ripples and waves slightly, possibly due to gravitational interactions with satellite galaxies like the Large Magellanic Cloud. These subtle distortions provide clues about how galaxies influence each other over cosmic distances. There are likely billions of white dwarfs scattered throughout the Milky Way. These stellar remnants represent the final evolutionary stage of medium-sized stars like our Sun. Over trillions of years, they will gradually cool and fade into black dwarfs, although the universe is not yet old enough for any black dwarfs to exist. The Milky Way contains thousands of known exoplanets. Many were discovered by missions such as Kepler and TESS. These discoveries reveal that planetary systems are common, suggesting that the processes that formed our solar system are not unique. The galaxy's interstellar medium is composed of gas, dust, cosmic rays, and magnetic fields. Although incredibly sparse compared to Earth's atmosphere, this medium plays a crucial role in star formation and galactic chemistry. Massive stars in the Milky Way often end their lives as supernovae, briefly outshining entire galaxies. These explosions send shockwaves through space, compressing nearby gas clouds and sometimes triggering the formation of new stars. The Milky Way contains numerous open star clusters. Unlike globular clusters, open clusters are loosely bound groups of younger stars that formed from the same molecular cloud. Over time, gravitational interactions cause these clusters to disperse. Our galaxy likely hosts hundreds of millions of stellar mass black holes. Most are invisible unless they interact with a companion star, drawing in gas that heats up and emits X-rays detectable by telescopes. The Milky Way's future merger with the Andromeda Galaxy will not likely result in widespread stellar collisions. Despite the dramatic imagery often shown, stars are so far apart that direct collisions are extremely unlikely. Instead, gravitational interactions will reshape both galaxies over billions of years. The galaxy's chemical composition has evolved over time. Early stars were made almost entirely of hydrogen and helium. Later generations contain heavier elements produced by earlier stars, meaning our Sun is richer in metals than the oldest stars in the galaxy. The Milky Way emits a faint glow even outside the visible spectrum. In radio wavelengths, its spiral structure becomes more apparent, allowing astronomers to map regions hidden behind thick dust clouds. Our galaxy's name in many cultures reflects its appearance as a luminous river in the sky. Various mythologies describe it as spilled milk, a celestial path, or a river of souls, demonstrating how deeply the Milky Way has influenced human imagination. The Milky Way's total mass, including dark matter, is estimated to be about 1 to 2 trillion times the mass of the Sun. However, only a small fraction of that mass is in the form of visible stars and gas. The solar system's motion through the Milky Way exposes it to varying cosmic environments over time. As we pass through spiral arms or denser regions, the rate of nearby supernova may change, potentially influencing Earth's climate and biological history. Over extremely long timescales, the Milky Way will gradually exhaust much of its star-forming gas. Star formation will slow, and the galaxy may evolve into a quieter, redder system dominated by older stars. Even though the Milky Way seems permanent and majestic, it is just one chapter in a dynamic cosmic story. It formed from ancient gas clouds, grew through mergers and star formation, and will eventually merge with Andromeda, transforming into something entirely new yet still part of the ever-evolving universe. The Milky Way did not form all at once, but assembled gradually through hierarchical growth. In the early universe, smaller clumps of matter collapsed under gravity and merged together. Over billions of years, these fragments combined to build the large spiral galaxy we inhabit today. Evidence for this process is preserved in the motions and chemical compositions of stars, which act like fossils recording the galaxy's formation history. One of the most important missions for mapping our galaxy is the European Space Agency's Gaia spacecraft. Gaia has measured the positions and motions of more than 1 billion stars with extraordinary precision. By tracking how these stars move, astronomers can reconstruct past collisions and better understand the Milky Way's structure and evolution. The Milky Way's stellar populations are often divided into Population I and Population II stars. Population I stars, like our Sun, are relatively rich in heavy elements and are found mostly in the disk. Population II stars are older and metal-poor, residing mainly in the halo and globular clusters, offering a glimpse into the galaxy's earliest epochs. Near the center of the Milky Way lies a region called the Central Molecular Zone. This area is packed with dense molecular clouds, extreme temperatures, and intense magnetic activity. Star formation here occurs under conditions far more violent than those in the quieter spiral arms, making it an important laboratory for understanding extreme astrophysical processes. The Milky Way contains hypervelocity stars, rare stars, traveling so fast that they can escape the galaxy's gravitational pull. Some of these stars are believed to have been accelerated by close encounters with the supermassive black hole at the galactic center. Their trajectories provide valuable clues about the black hole's influence and the galaxy's gravitational field. The galaxy is filled with interstellar dust grains made of carbon, silicon, oxygen, and heavier elements. These tiny particles, often no larger than smoke grains, play a crucial role in cooling gas clouds and enabling star formation. They also scatter and absorb starlight, creating the dark lanes visible in images of spiral galaxies. The Milky Way's spiral structure is still being refined as new data becomes available. For decades, astronomers debated how many major spiral arms the galaxy has. Radio observations and stellar mapping suggest at least 4 primary arms, but the exact details remain an active area of research. At radio wavelengths, astronomers observe powerful masers within star-forming regions. These naturally occurring microwave amplifiers emit intense radiation that can be used to measure distances across the galaxy with remarkable accuracy. By studying masers, scientists can map the Milky Way's structure more precisely. The Sun is currently passing through a region of space known as the local interstellar cloud. This cloud is part of a larger cavity called the local bubble, a region of lower density gas likely carved out by ancient supernova explosions. These past stellar deaths shaped the environment surrounding our solar system. The Milky Way's gravitational field influences the motion of comets in the Milky distant Oort cloud surrounding our solar system. As the Sun orbits the galaxy, tidal forces from the galactic disk and nearby stars can disturb comets, occasionally sending them inward toward the inner solar system. Some stars in the Milky Way form binary or multiple star systems. In fact, many stars are not solitary like our Sun. Binary interactions can produce fascinating phenomena, including X-ray binaries and Type Ia supernova, which are critical for measuring cosmic distances. The Milky Way contains magnetars, a rare type of neutron star with incredibly powerful magnetic fields. These objects can release enormous bursts of energy in fractions of a second. Studying magnetars helps scientists understand matter under some of the most extreme conditions in the universe. In addition to stars and gas, the Milky Way hosts vast numbers of brown dwarfs. These objects are sometimes called failed stars because they lack enough mass to sustain hydrogen fusion in their cores. Brown dwarfs bridge the gap between planets and stars and may be extremely numerous throughout the galaxy. The galaxy's stellar disk is embedded within a diffuse corona of hot gas that emits X-rays. This hot halo may act as a reservoir of material that can cool and fall back into the disk, fueling future star formation. Observations of this corona help astronomers estimate the galaxy's total mass. The Milky Way's center experiences occasional bursts of star formation, known as starburst episodes. These bursts can be triggered by inflows of gas or interactions with satellite galaxies. Although the galaxy is relatively calm now, its past likely included more active periods. Astronomers have discovered that the Milky Way's bar rotates as a rigid structure, influencing the orbits of stars in the inner galaxy. This rotation redistributes angular momentum and helps shape the spiral arms, playing a key role in the galaxy's long-term evolution. The galaxy's oldest known star clusters provide age estimates for the Milky Way itself. Some globular clusters are more than 12.5 billion years old, suggesting that the galaxy began forming very early in cosmic history. The Milky Way's disk contains a gradient in chemical composition. Stars closer to the center generally contain more heavy elements than those farther out. This gradient reflects the higher rate of star formation and supernova enrichment in the dense inner regions. Astronomers believe that stellar migration occurs within the Milky Way. Over time, stars can move inward or outward from their original birthplaces due to gravitational interactions. This means the Sun may not be in the exact region where it originally formed billions of years ago. The Milky Way has likely experienced close encounters with dwarf galaxies that did not fully merge but passed nearby, gravitationally stirring its disk. These flybys can create ripples and waves in the stellar distribution, some of which are still detectable today. Cosmic dust within the Milky Way is responsible for the reddish appearance of distant stars. Blue light is scattered more easily by dust, while red light passes through more effectively. This phenomenon, known as interstellar reddening, must be accounted for when measuring stellar properties. The Milky Way's central black hole occasionally consumes gas clouds or stars that wander too close. When this happens, the infalling material heats up and emits intense radiation before crossing the event horizon. These events provide opportunities to study black hole physics in action. Our galaxy is surrounded by a population of ultra-faint dwarf galaxies. These tiny galaxies contain very few stars, but are rich in dark matter. They are among the most dark matter-dominated objects known and help researchers test theories about dark matter behavior. The Milky Way's spiral arms may slowly change shape over time. They are not permanent structures, but dynamic patterns created by gravitational interactions. As stars orbit the galaxy, they move in and out of these arms, spending only part of their lives within them. Far in the future, long after the merger with the Andromeda Galaxy, the resulting galaxy, sometimes nicknamed Milkomeda, will gradually exhaust its remaining gas. Star formation will slow dramatically, and the night sky would grow darker as fewer new stars are born. Despite all we have learned, much about the Milky Way remains mysterious. From the true nature of dark matter to the detailed history of past mergers, our home galaxy continues to challenge astronomers. Every new observation adds another piece to the puzzle, revealing that even though we live inside it, the Milky Way is still largely uncharted territory. The Milky Way's mass is distributed unevenly, with most visible matter concentrated in the disk and bulge, while most of the total mass resides in the dark matter halo. This imbalance means that what we can see stars, gas dust accounts for only a small fraction of the galaxy's true gravitational influence. The invisible dark matter halo acts like a massive scaffold, holding the luminous parts of the galaxy together. The galaxy's rotation period varies depending on distance from the center. While our Sun takes roughly 230 million years to complete one orbit, stars closer to the core can orbit in just tens of millions of years. Meanwhile, stars far in the outer disk take longer but still move faster than expected, reinforcing evidence for dark matter's presence. The Milky Way's spiral arms are sites of massive stellar associations, known as OB associations. These are loose groupings of extremely hot, short-lived O-type and B-type stars. Because these stars burn out quickly, their presence indicates very recent star formation, making OB associations valuable markers of active regions within the galaxy. Some regions of the Milky Way glow intensely in infrared light due to warm dust heated by nearby stars. Infrared astronomy has allowed scientists to peer through thick dust clouds that block visible light, revealing hidden clusters and complex structures that would otherwise remain invisible. The galaxy contains planetary nebulae, glowing shells of gas expelled by dying stars, similar in size to our Sun. Despite the name, planetary nebulae have nothing to do with planets. Early astronomers gave them that name because their round shapes resembled planets in small telescopes. Within the Milky Way, there are regions called stellar nurseries, where protostars are actively forming. In these areas, gravity pulls material inward, forming spinning disks of gas and dust around young stars. Over time, these disks can coalesce into planets, moons, asteroids, and comets. The Milky Way's central bulge has a peanut-like or X-shaped structure when viewed in certain wavelengths. This unusual shape likely results from the dynamical evolution of the galactic bar, which redistributes stars into elongated orbits over billions of years. The galaxy contains vast filaments of cold gas that stretch for hundreds of light years. These filamentary structures act as the backbone of star formation, channeling material into denser knots where new stars ignite. Observations suggest that filament formation may be a universal step in how galaxies create stars. The Milky Way emits a faint background glow in gamma rays. Some of this radiation may come from pulsars, supernova remnants, and interactions between cosmic rays and interstellar gas. There is also ongoing research into whether part of this gamma ray glow could be linked to dark matter interactions. The solar system's orbit around the Milky Way is not perfectly circular, but slightly elliptical. As a result, our distance from the galactic center changes slightly over time. However, these variations are small compared to the vast overall scale of the galaxy. Some stars in the Milky Way move in retrograde orbits, meaning they orbit the galaxy's center in the opposite direction of most stars. Many of these stars are thought to have originated in dwarf galaxies that merged with the Milky Way long ago. The Milky Way likely experienced a major merger around 8 to 10 billion years ago, with a galaxy sometimes referred to as Gaia Enceladus. Evidence for this ancient collision comes from stellar motion data, which shows a distinct population of stars with unusual orbits and compositions. The galaxy's interstellar medium contains complex organic molecules, including carbon-based compounds. These molecules form in cold molecular clouds and demonstrate that the chemical building blocks of life are widespread throughout the Milky Way. Some parts of the Milky Way are so dense with stars that the night sky on a planet in those regions would be dramatically brighter than ours. In the inner galaxy, neighboring stars can be much closer together, creating a sky filled with brilliant points of light. The Milky Way's disk contains radial migration patterns, meaning stars can drift inward or outward from their birth radii over time. This mixing process complicates efforts to trace where specific stars originally formed. There are regions in the galaxy where star formation has largely ceased. These areas, dominated by older red stars, give hints about how galaxies gradually age and transition from active star-forming systems to quieter ones. The galaxy contains tidal streams not only from disrupted dwarf galaxies, but also from globular clusters. As these clusters orbit the Milky Way, gravitational forces slowly strip stars away, forming long, thin streams that trace their orbital paths. The Milky Way's gravitational pull affects nearby galaxies within the local group. Its mass contributes to the overall dynamics of the group, influencing how galaxies, like the Large Magellanic Cloud, move through space. High-mass star-forming regions often produce strong stellar wind streams of charged particles, flowing outward from young, hot stars. These winds can sculpt surrounding gas into intricate shapes, forming pillars and cavities within nebulae. The galaxy's central region contains dense star clusters that may eventually spiral inward due to gravitational interactions, potentially feeding the supermassive black hole with additional material over cosmic timescales. The Milky Way is gradually growing by accreting not only stars and gas, but also dark matter. As smaller systems merge with it, their dark matter halos combine with the Milky Way's own halo, increasing its total mass. The distribution of star ages across the Milky Way reveals that the inner regions formed stars earlier and more rapidly than the outer regions. This inside-out growth pattern is common among large spiral galaxies. The Milky Way contains thousands of known supernovae, remnants expanding shells of gas left behind after massive stars explode. These remnants can persist for tens of thousands of years, enriching the interstellar medium with heavy elements. The galaxy's disk is populated by both short-lived massive stars and long-lived low-mass stars. Because low-mass stars burn their fuel slowly, many of the earliest ones formed in the galaxy may still be shining today. Gravitational microlensing events occur when a massive object in the Milky Way passes between Earth and a distant star, briefly magnifying the background star's light. These events help astronomers detect otherwise invisible objects like rogue planets or faint stars. The Milky Way is expected to continue forming stars for several billion more years, as long as sufficient gas remains. However, once that gas supply diminishes, the galaxy's appearance will slowly shift toward redder hues as older stars dominate. Although we often picture the Milky Way as serene and unchanging, it is a dynamic, ever-evolving system. Stars move, gas flows, black holes feed, and galaxies merge. Our home galaxy is not a static backdrop, but an active participant in the unfolding story of the universe, constantly reshaping itself across unimaginable spans of time. The Milky Way's stellar disk contains subtle spiral density waves that move through it like ripples in water. These waves are not made of fixed groups of stars. Instead, they are patterns of higher density that stars pass through as they orbit the center. As gas clouds enter these denser regions, they compress and trigger new star formation, helping maintain the spiral structure over long timescales. The galaxy's outer edges are faint and difficult to define precisely, while the bright stellar disk extends about 100,000 light-years across. Faint stars and gas stretch much farther. Beyond that lies the enormous dark matter halo, which extends several times farther still, making the Milky Way much larger than it appears in visible light. The Milky Way contains regions of intense radio emission caused by energetic electrons spiraling along magnetic field lines. This radiation, known as synchrotron emission, reveals the presence of large-scale magnetic structures that weave through the galaxy and influence the movement of charged particles. Some stars in the Milky Way are arranged in moving groups collections of stars that share common velocities through space. These groups may be remnants of dissolved star clusters or debris from past galactic mergers. By studying their motion, astronomers can trace back events that occurred billions of years ago. The galaxy hosts X-ray binaries, systems in which a neutron star or black hole pulls material from a companion star. As the material spirals inward, it heats to millions of degrees and emits powerful X-rays. These systems provide insight into how compact objects grow and interact with their environments. The Milky Way likely contains more than 150 known globular clusters, with possibly more still undiscovered behind dense dust clouds. Each globular cluster contains hundreds of thousands of tightly packed stars, many of which formed at nearly the same time early in the galaxy's history. The galaxy's chemical evolution is ongoing. Each generation of stars fuses lighter elements into heavier ones, and when those stars die, they release enriched material into space. Over billions of years, this recycling process has increased the abundance of elements necessary for rocky planets and life. Some parts of the Milky Way's halo contain stellar streams that wrap around the galaxy like ribbons. These streams can span tens of thousands of light years and are relics of galaxies or clusters torn apart by gravitational forces. Their shapes and motions help scientists map the galaxy's gravitational potential. The Milky Way's central supermassive black hole, Sagittarius A*, occasionally flares when it consumes small amounts of gas. These flares can be observed in infrared and X-ray wavelengths, offering real-time glimpses of matter spiraling toward the event horizon. The galaxy's disk is peppered with superbubbles formed by clusters of massive stars. When several massive stars go supernova in close proximity, their shockwaves combine to carve enormous cavities in the interstellar medium, reshaping the surrounding gas distribution. The Milky Way's gravitational pull affects nearby satellite galaxies, stripping them of gas and stars. Over time, these interactions can transform gas-rich dwarf galaxies into gas-poor systems, altering their ability to form new stars. There is evidence that the Milky Way's bar structure may have grown stronger over time. As it evolved, it could have redistributed stars within the inner galaxy, influencing the formation of the bulge and altering orbital paths of stars near the center. The galaxy contains cosmic dust lanes that appear as dark streaks against bright star fields. These lanes are thick clouds of gas and dust that block visible light, creating dramatic contrasts in astronomical images. The Milky Way's interstellar gas exists in multiple phases: cold molecular clouds, warm neutral hydrogen, warm ionized gas, and extremely hot ionized plasma. These phases coexist and interact, creating a complex ecosystem within the galaxy. Some stars orbit the Milky Way, far above and below the main disk. These halo stars often have highly elliptical orbits and may represent remnants of ancient mergers, preserving clues about the galaxy's formative years. The galaxy's spiral arms rotate at a different speed than individual stars. This means stars drift in and out of spiral arms during their lifetimes, experiencing alternating periods of denser and quieter galactic environments. The Milky Way contains numerous pulsars, rapidly spinning neutron stars that emit beams of radiation. When these beams sweep past Earth, they appear as precise pulses. Pulsars serve as cosmic clocks and help astronomers test theories of gravity. Interstellar shocks from supernova explosions can trigger star formation by compressing nearby gas clouds. In this way, the death of one star can help give birth to many new ones, linking stellar life cycles across generations. The Milky Way's disk contains a subtle flare at its outer edges, meaning it becomes slightly thicker farther from the center. This flare may result from gravitational interactions with satellite galaxies or the distribution of dark matter. Some of the oldest stars in the Milky Way are found in the halo and bulge. These ancient stars have extremely low metallicity and may have formed shortly after the first generation of stars enriched the early universe. The galaxy's motion through space is influenced by the gravitational pull of other members of the local group. Eventually, this mutual attraction will lead to its merger with the Andromeda Galaxy, dramatically reshaping both systems. The Milky Way's star formation rate has fluctuated over time. Periods of increased star formation may have been triggered by mergers or gas inflows, while quieter periods reflect times when gas supplies were lower. The galaxy contains regions of ionized hydrogen known as H2 regions. These glowing clouds surround young, hot stars whose ultraviolet radiation strips electrons from hydrogen atoms, causing the gas to shine brightly. Our solar system is currently located in a relatively low-density region between major spiral arms. This position may provide some protection from the higher supernova rates found within dense arms. Over billions of years, gravitational interactions within the Milky Way will gradually scatter stars into new orbits. The orderly spiral structure we see today will slowly evolve, even before the eventual merger with Andromeda. The Milky Way is just one example of a spiral galaxy, yet it serves as our primary laboratory for understanding how galaxies work. Because we are inside it, we can study individual stars in extraordinary detail, something far more difficult in distant galaxies. Despite centuries of observation, much of the Milky Way remains hidden behind dust or too distant to measure precisely. With each new telescope and mission, we uncover more of its structure, history, and complexity, revealing that our home galaxy is far more dynamic and intricate than once imagined.